probability theory, the gamma distribution is a generalization of the exponential distribution. While an exponential random variable represents the waiting time for the first success, the gamma random variable represents the total waiting time for multiple successes. When we introduced the exponential distribution, we viewed it as the continuous analog of the geometric distribution. Likewise, we can now say that the gamma distribution is the continuous analog of the negative binomial distribution. Firstly, we can visualize this. Let t denote the waiting time until the nth event occurs. Graphically, we can look at this. This is the timeline t. First event occurs somewhere here. Second event occurs somewhere here. It goes until the nth event occurs somewhere here. This time is basically the small t. So we will find the distribution of this t. Just as we did in the derivation of exponential distribution, we will find the CDF first, then differentiate it to find the PDF. So CDF of t can be written as probability of capital T less than or equal to small t. This is the probability that the waiting time until the nth event is less than t time units. It is equal to saying 1 minus probability of t greater than or equal to small t. What is the meaning of this part? The waiting time capital T is greater than some small t only if there are less than n events in the interval 0 to t. That we can rewrite like this: 1 minus probability of less than n events in 0 to t intervals. It can be rewritten like this: 1 minus probability of 0 event or 1 event or 2 events till n minus 1 event in 0 to t interval. We can rewrite this part in Poisson distribution, where lambda is lambda times t because we are looking in t time units. So we can rewrite this as 1 minus summation n takes value 0 because we are starting from 0 event till n minus 1. Lambda t power n e power minus lambda t all divided by n factorial. So we are summing from 0 to n minus 1. The first term will be e minus lambda t. So we can rewrite this like then from n1 to n minus 1. This is basically the CDF. If I differentiate this function, I will get the PDF. So PDF is basically equal to differentiation of this with respect to t will be 0. This will be equal to lambda e power minus lambda t, then minus 1 by n factorial. Then for this part we will use the product rule. From here I can take out this common term. Here I am writing n factorial as n times n minus 1 factorial. I can cancel this both. So now we will expand this from 1 to n minus 1. First term will be lambda t minus 1 second term will be lambda t square by 2 factorial plus minus lambda t plus lambda t cube divided by 3 factorial minus lambda t 2 divided by 2 factorial. It will go like this till we will get the final term as lambda t power n minus 1 divided by n minus 1 factorial minus lambda t power n minus 2 divided by n minus 2 factorial. So we can cancel many terms in this. I can cancel this both. I can cancel this both. So these all middle values will be cancelled out, but we will be left with these two terms. So we can rewrite this equation as minus 1. So we can cancel this and this. So we will be left with this can be written as, I am taking lambda together, so it will be lambda power n t power n minus 1 e minus lambda t divided by n minus 1 factorial. This n minus 1 factorial we can write in gamma function like this, gamma n. So finally we will get with two parameters n and lambda. Here n is the number of events or success, failure, anything which you are waiting to occur. 2 success, 3 success, n success, it can be anything. And 1 by lambda is basically the mean waiting time until the first event occurs. So as we started, this is the generalization of the exponential distribution for multiple success. If we consider only one success, then this function is equal to exponential distribution. For example, if I substitute n equal to 1, I will get lambda e power minus lambda t. So this is nothing but exponential distribution. So gamma 1 lambda is equal to exponential with lambda. This is the relation between the gamma and exponential distribution. So if we sum n independent exponential random variable with parameter lambda, you will get a gamma random variable with parameters n and lambda. So we can use this property and derive the Mgf and everything very easily. We know the Mgf of exponential distribution is given as lambda divided by lambda minus t. So if I want to find the Mgf of sum of two independent exponential random variable, it is equal to saying expectation of e power t times x1 plus x2, that is equal to saying expectation of e power tx1 times expectation of e power tx2. So this is equal to saying lambda divided by lambda minus t times lambda divided by lambda minus t. This is equal to saying lambda divided by lambda minus t square. Here there is only two independent exponential random variable. If I want to find the Mgf of sum of n independent exponential random variable, then I can write this like lambda divided by lambda minus t whole power n. So this is the Mgf of gamma distribution. Now we can easily differentiate this and find different moments. So we can try the first and second moment here. If first derivative of Mgf is equal to, we will use both chain rule and quotient rule to differentiate this. If I set t equal to 0 here, then this whole term will go as 1. So we are left here with n. Then here it will be lambda divided by lambda square. So finally we will have n by lambda. So this is the first moment of gamma distribution. Whereas the first moment of exponential distribution was 1 by lambda, because we are only looking for first event or one success. Here we are looking the multiple success or multiple event, that's why there is n here. In the similar way, the variance of exponential distribution was 1 by lambda square. The corresponding variance for gamma distribution is n by lambda square. Now we can talk little bit about the shape of the gamma distribution. It depends upon both the n and lambda. N is basically the number of events and 1 by lambda is the mean waiting time for the first event. Here we can consider two cases. Firstly, we will fix the value of n and we will see how the changes in 1 by lambda make changes in the graph. Secondly, we will fix the value of 1 by lambda and we'll see how the changes in n makes changes in the graph. For example, in first case we are assuming n equal to 3. It means there are basically 3 events. And I can draw gamma distribution like this. Here n is 3, it means we are waiting for 3 events to occur. Then we have a greater probability of our waiting time x being large if our mean waiting time 1 by lambda until the first event is large. So it makes sense then for fixed n, as 1 by lambda increases, the probability moves to the right. Now we can consider the second case where we are fixing the mean waiting time 1 by lambda and changing the number of events. Here the mean waiting time until the first event is fixed, that is 3. Then we have a greater probability of our waiting time x being large if we are waiting for more events. So it makes sense that for fixed mean waiting time, as n increases, the probability moves to the right. Now we will solve one problem and see how this is working. So the question says that engineers designed 2 fuel pumps for a space shuttle, one active, the other in reserve. If the first pump fails, the second is automatically brought online. According to manufacturer's specifications, each pump is expected to fail once every 100 hours. So what are the chances that both pumps, the complete fuel system, would not remain functioning for the first full 50 hours? So we are given that the life of the pump on an average is 100 hours. So expectation is 100. This is for each pump. Basically the life of each pump follows an exponential distribution. Then the mean of the exponential distribution is equal to 1 by lambda. It implies that lambda is equal to 1 by 100. And we are looking 2 events, basically 2 failures. So n is 2. So we got the value of n and lambda. So this is basically following gamma 2 1 by 100. So we can put this value into this equation. So we will get 1 by gamma 2, then lambda power n x power n minus 1 e power minus lambda x. So gamma 2 is basically 2 minus 1 factorial. So it is 1 again. This is x itself. So we can rewrite this function as 1 by 10,000 x e power x by 100. So the probability that both fuel pump fail before 50 hours can be written like this. Here we will use integration by part. Basically it is equal to saying integration of u dv equal to uv minus integration of v du. So in this case we can assume x is equal to u, then dx by du is 1. That implies dx is equal to du. And this part we can consider as dv. So dv is equal to e power minus x divided by 100. It means v is equal to minus 100 e power minus x divided by 100. Because if we differentiate this, we will get this. Substituting these values into equation, we can finally write probability of x less than 50 is equal to, I'm taking this constant outside, u is basically x, v is basically minus 100 e power minus x divided by 100, then minus integration of v du is basically equal to dx. Here x will take values from 50 to 0. We can solve this part first. So 50 multiplied by minus 100 e power minus 1 by 2 minus 0. So this will be equal to minus 5000 e power minus. Now we can integrate this part. Here we can take this constant outside, so it will be positive. For this I will use substitution. Let u is equal to x by 100, then du dx is equal to 1 by 100, dx is equal to 100 times du. So instead of dx we can write this. So I can write this all together 100 e power minus u 100 du. This I can take outside. So 10,000. Integration of this is very easy. Minus e power minus u. Substituting the value of u, when x takes 50, this becomes minus e 1 by 2. When x takes value 0, this becomes minus 1. Now we can put this in our earlier equation. So it will be equal to 1 by 10,000 minus 5,000 e power minus 1 by 2 plus 10,000 1 minus e power minus 1 by 2. So multiplying all this by this constant, we will get minus 1 by 2 e power minus 1 by 2 plus 1 minus e power minus 1 by 2. So this can be written as 1 minus 3 by 2 e power minus 1 by 2. This is equal to almost 0.09. So there is 9% chance that the fuel system completely will fail before 50 hours. So in this video we started by the definition of gamma distribution. We tried to connect with geometric distribution, negative binomial distribution and exponential distribution. By using the Poisson distribution, we derived the density of gamma distribution. Then we derived it is Mgf from the Mgf of exponential distribution. Then we talked a little bit about the shape of the gamma distribution with respect to n and lambda. Then finally we tried to solve one problem. So please watch the videos and subscribe my channel. In the next video we will talk about the chi-square distribution. It is also a variant of gamma distribution.